So let's add another integration technique to our toolbox. So we've looked at regular old integration, so like basic stuff where you just kind of have to recognize the trig derivatives. We've looked at inverse trig integrals, so when the antiderivative is an inverse trig function. We've done U substitution, which is kind of like the integral version of the chain rule, right? It's kind of backwards chain rule. So now we're going to look at something else that's kind of backwards product rule from differentiation. So integration by parts works in very specific situations. So for instance, if I gave you an integral that looked like this, the integral of x squared times the sine of x dx, right? Well, what we know right now, right? So it's not just a straight up integral. We don't recognize this as the derivative of a specific function, so we can rule that out. So the only other way that and it doesn't look like it's an inverse trig because there's no fractions in here, right? If there's no rational part of it, can't possibly be an inverse trig integral. So the only other option we have right now is to try U substitution, backwards chain rule, right? So we have two options that we could pick for U. So say we pick U to be x squared, then our du would be equal to 2x dx. Okay, well that means that the sine of x doesn't fit, so there's no way for me to replace that, and I have an extra x in my dx, so okay, that's not going to work. Okay, so then the other option would be, well, what if I just make the u the sine of x? Well, then my du is cosine of x dx. So I could replace the x squared by solving and making u, like solving the u for x, so that would make the arcsine of u is equal to x, so we had arcsine squared, and now I just feel like we're making it more complicated, so like that's not working either. So when we have this product going on, that might be an indication that we might be doing integration by parts, especially between two functions that really have nothing to do with each other, right? X squared and sine of x aren't related in any way. So when those types of functions are being multiplied, that's a great indication that we want to use integration by parts. So our integration by parts formula, and I'll show you where it comes from, because otherwise you're like, why? Why is that the formula? I will often abbreviate this as IBP, integration by parts. So what this says is that, right, let U and V be functions that have continuous derivatives, which basically means that both of them are differentiable. So if that condition is met, we have that the integral of u dv is equal to the functions u times v minus the integral of v du. Okay, so let's talk about this. So the initial problem setup is there on the left, so it's the integral of u times dv. So that means it's the integral of some u function times the derivative of some v function. And if that is the setup, we have that, okay, you find the two functions u and v, and you multiply them together, and then you subtract the integral of the v function times the derivative of the u function. So I'm not going to do like a super formal proof. I'm just going to kind of go through a simpler explanation of where does this come from. So what this comes from is the product rule. Right? So we know that the product rule, and I'm even going to use u and v. So we'll use u of x times v of x. I need more room. And if I really want to be good, I could be color coding all of this. So let me cheat and do this a little bit. Okay, so we know that the product rule is the derivative of the first. So this is u prime of x times the second Don't ask why most books use u's and v's for this. I have no idea, but we do. So if your u's and v's look very similar, like notice how I always put a tail on my u's so they never look like v's, just pick different letters, like pick u and w or f and g, it doesn't matter. Anyway, back to product rule, and then it would be the derivative of v with respect to x times u of x. Okay, so if I take my product rule, what I'm going to do is I'm going to integrate the whole thing. So I'm going to integrate each part of it. So now when I integrate things, I need to throw some dx's on the end. So I'm going to throw a dx here, here, and here. So when I integrate the left-hand side, right, the integral and the derivative are inverses, so they just cancel each other out. And I'm going to be left with this stuff. And then I can't take, right, I'm just going to leave these two the same. It's just equal to those integrals. So now all I'm going to do is I'm going to subtract this integral to the other side. Okay. So when I do this, I'm going to get u times v minus, I'm going to cheat just so it's color-coded already for me, minus the integral of u prime times v of x equals this integral. Now this is backwards to the way that I wrote it. That should be an equal sign, not a minus sign. Ready? So if we kind of just drop the x's, right, the x's are just kind of implied, we get u times v minus the integral, right, u prime, right, that's du over dx. So if I replace the u prime with du over dx, and then I have this dx here at the end, these are going to cancel out, so I'm going to be left with my v function. I really wish I'd moved this down. There we go. Times u times my du, right, because that's going to be left over there, equals, right, I can think of this as being the same way, right? V prime is really dv over dx, right? And then my dx's are going to cancel, so then I'm going to have the integral of u times dv, right? Which is just, I flipped it, right? I usually wrote the initial integral on the other side, right? It's just backwards of what we wrote right there. So the integration by parts formula directly comes out of the product rule for differentiation. So what I want to do is, let's first go back. Actually, before we go back to that first problem, because that's a little bit more intense, let's just do a more basic problem as an example. So we want to integrate x times e to the x dx. So I like to make like a little chart when I do these. So you want to pick your u and your dv, right? So if we're looking here, right, this is representing what we have right here. So we want to pick a u function, and we want to pick out which one is our dv. So I'm going to write u equals and dv equals. So you want to be careful here. So if you have a polynomial portion like x, you typically want to pick the polynomial portion to be your u, because then when we go to differentiate both sides, my du, right, the derivative of x is 1, so I get just that du is dx, not du. Right, so in other words, I'm canceling down the powers, and that usually makes it easier to integrate later. So your dv, you want to pick something that is easier to integrate. And e to the x is a great choice for dv because the derivative, right, so this whole thing is going to be our dv. This is going to become our u. So if I integrate both sides now, right, the integral of dv is just v. and the integral of e to the x is e to the x. So now when I'm going to go to plug in my formula here, I really wish I'd written this backwards. So ready? We're just going to, actually, we're going to copy down the way I wrote it earlier. Bum-ba-da-dum. The beauty of the iPad, right? So we have our integral, right? So now our u times v is going to be x times our v function, which is e to the x, minus the integral of v, so that's e to the x, times du, which is just dx. Move that over, draw myself a little like line here to separate the work. Okay, right, so then the next line would be x times e to the x minus, okay, well, the integral of e to the x is just e to the x, and then I'd put my plus c on because it's an indefinite integral. And that's not the color I wanted to go away. No. Okay, so then we are going to have that as our final answer. Okay, so let's do a couple more examples. So I want to cover probably 2 or 3 more problems. So let's do one more basic problem before we kind of get into the more advanced stuff. So if we take the integral of x times cosine of x dx, right, again, right, just since we're first quote unquote learning this, I'm just going to copy my formula down, right, so we have it right in front of us. So right, the first step is to pick your u and your dv. So your u, remember, it's a great way to pick your u if you can make your powers reduce and you can kind of work on getting the function to go away. So I have an x, so the easiest choice for u is to pick the x. I'm going to differentiate that, so I'm going to get that du is just dx again. Perfect. So then the other part, right, that's going to be my dv. So then if I integrate both sides of that to get what my v function is, the integral of cosine is just sine of x. So now if I just follow my formula, that integral equals u is equal to u times v, so I'm going to get x times the sine of x minus the integral of my v function, so that's going to be sine of x times my du, which is dx here. Right, so then my next line would be x times sine of x minus the integral of sine of x is just negative cosine of x, right, plus c because it's an indefinite integral, and then I'm going to resolve that double negative to simplify. Okay. So let's actually look back at that initial problem I wrote to kind of start our discussion. So we had x squared sine of x dx. So this is a great problem to use for integration by parts because you have the product of 2 functions and they're not related to each other in any way. So a normal u substitution is not going to work. So I'm going to pick my u here to be x squared, which means my du is going to be 2x dx. Now the great thing about this is you don't need to solve for anything here, right? It's not like a normal like basic u sub where you have to solve for dx or anything. And then my dv is just going to be everything else that's left in the problem. So sine of x dx, integrate both sides. So my v function is going to equal negative cosine of x. I'm going to actually shrink this stuff, put it to the side. So then if I'm following my integration by parts formula, I get u times v, so I get x squared times negative cosine of x minus the integral of v du. So if I plug in v, I get negative cosine of x, and if I plug in my du, I get 2x dx. Okay, so if we simplify things, this becomes negative x squared cosine of x right? I have this double negative here, so I'm going to make it plus 2x cosine of x dx. So what I technically need to do here, right, this is another integration by parts. Right, so I could do it again because, right, it's an x function, it's a polynomial times a cosine, so those two things are unrelated, but I'm going to cheat a little bit because, look, we did this, right? We did x cosine of x. This is just 2 times that. So I'm going to cheat a little bit instead of doing it twice, right? That's just 2 times the integral of x cosine of x dx. And I already know what that answer is. It's, right, it's in that green box right above. So that's x sine of x plus cosine of x plus c. Right, and if I distribute the 2, I get 2x sine of x plus 2 cosine of x, and then 2 times c is just another constant, so we're just going to leave that as a constant. So I'm only going to do one more problem in this video, and it's to show you something kind of cool. So integration by parts can also help you figure out how to integrate functions that you otherwise don't know how to integrate. Right? So if you're just given the integral of the natural log of x dx, right, you don't know what the integral of natural log of x dx is, but we can actually pull a little trick and use integration by parts to do that. Right? So a trick for integration by parts is if you think you might be using that as your integration technique and you don't know how to integrate part of it, if you don't know how to integrate something, that guarantees that it's your u, right? So I don't know what the integral of the natural log of x is, so it can't be my dv, because if I knew that, I wouldn't need integration by parts. I would just write down the answer. So I'm going to make this my u since I don't know how to integrate it. So when I take my derivative, my du is going to equal 1 over x dx. So then the only other portion of my original integral that I have not covered yet is the dx. So I'm going to let dv equal dx. And then if I integrate both sides with respect to their variables on each side, right, the integral of dv is just v. The integral of dx is just x. So when I apply integration by parts, I get u times v. So I'm going to get the natural log of x times x minus the integral of v times du. Okay, so if I'm going to flip the order here so it looks a little nicer to write. Now if I simplify in here, x times 1 over x is 1, so I'm going to be left with dx here, and then the integral of dx is just x, and then you throw in your constant of integration plus c. So this tells us that the integral of the natural log of x dx, right, is x ln of x minus x plus c. So, right, that's a new integration formula. So you could memorize that and use it whenever you need to, or, right, you can always just know that you can find it